Alright, so now we're going to take a look at 10b. So f of x is equal to x over x squared minus 1. So I'm going to take two derivatives. We're going to have to use quotient rule twice. And it's going to be a little bit not fun. So f prime of x is going to be low d high squared minus 1 minus high d low, which is x times 2x over x squared minus 1, which is x squared minus 2x squared, so minus x squared minus 1 over x squared plus 1, or I'm just going to put this minus out, x squared plus 1 over x squared minus 1. And also this right here should be a minus. I kind of jumped ahead to having a plus 1. But that's what we've got by the quotient rule. Low d high, and this x squared minus 1 is squared. Perfect. Okay, so next, f prime prime of x, same deal. Low d high, so x squared minus 1 squared times the derivative of the top, which is going to be minus 2x, minus high d low, and I already kept this minus here, so I should keep it the whole way through, minus x squared minus 1 times the derivative of the bottom, which is 2 x squared minus 1 times 2x, all divided by x squared minus 1 to the fourth. And the thing that's going to save you a little bit of sadness on these product rule problems is you can factor out, just by using quotient rule, you can factor out one of these things. So here's x squared minus 1, here's x squared minus 1 squared. So I can factor out the biggest power, and I get f prime prime of x is equal to x squared minus 1 times x squared minus 1 minus 2x minus, this 2 and this 2 make a 4x, so I have plus 4x x squared plus 1. So a little bit of algebra happened there. I combine the minus and the minus x squared minus 1 to a plus. I combine the 2 and the 2x together, and I have x squared minus 1 minus 1 to the fourth. So this cancels, with this. I get a cubed. And now I can do some distributing. I get minus 2x cubed plus 2x plus 4x cubed plus 4x, all divided by x squared minus 1 cubed. If I combine like terms, I get 2 x cubed plus 6x over x squared minus 1 cubed. And finally, that's equal to 2x, and I get x squared plus 3 divided by x squared minus 1 cubed. Great, so we have f prime and we have f prime prime. So now we're ready to find critical points and find where it's increasing, decreasing, where it's concave up, concave down. So looking at the original function, we have minus x squared plus 1 over x squared minus 1, all squared. So let me rewrite that. Equals minus x squared plus 1. Nothing to worry about there. That's always a negative on top because x squared plus 1 is always bigger than 1. And then I multiply it by minus 1. But on the bottom I have some factors, x minus 1 and x plus 1. But those things are being squared. So actually, this function always has to be negative. And you can do a sign chart on that if you want to, so let's go ahead and do it anyway. Minus 1, 1, infinity. 1 and minus 1 are your only critical points. But let's go ahead and see why this ends up being the case. So I have minus x squared plus 1. X squared plus 1 is always positive, so if I put a minus in front, that's always negative. And then same thing here. So I didn't need to do this distribution because I have x squared minus 1 squared. That would have been easier for me to work with. And that's always going to be positive. Again, because I'm squaring a number. So then f prime of x is literally always negative. So no matter where I'm at, this function is decreasing, which is pretty interesting. So this function is decreasing everywhere. And now I look back at f prime prime of x, which I forgot what it was now. 2xx plus 3, x squared plus 3, over x squared minus 1 cubed. Okay. So that's what I've got. And now what are the critical points of this? I get a critical point of 0 from the x on top, and of plus or minus 1 from the denominator. Right. So now I do a similar sign chart. So similar sign chart. I forgot to say this is decreasing from minus infinity to infinity, decreasing everywhere. Or I said it, but I didn't write it. And now let's take a look at the second derivative. So from minus infinity, let me give myself a little bit more space there. Minus infinity, minus 1, 0, 1 to infinity. What do we have? 2x, x squared plus 3, that's always going to be positive. X minus 1 cubed, x plus 1 cubed. Because I can factor that x squared minus 1 into x minus 1, x plus 1, and then cube those two things. So now let's take a look. So if I plug in a negative number, I get a minus. For this, if I plug in positive, I get positive for the 2x. For x minus 1 cubed, if I plug in something really small, I get a negative. If I plug in something between minus 1 and 0, I get a negative. If I plug in, say, a half, still negative. If I plug in something bigger than 1, now it's positive. For x plus 1, again, if I plug in like minus 2, I get a negative. If I plug in, say, minus a half, now it's positive, and once it's positive once, it stays positive forever. And now here, there was some confusion. We count the number of minus signs to determine the final sign, because the idea is you're multiplying this many numbers together. So I have a minus times a minus is a plus, times another minus is a minus here. Here I have a minus times a minus is a plus. Here I have one minus, and then here I have all pluses. So this thing is concave down on minus infinity to minus 1, together with 0 to 1, and concave up from minus 1 to 0, together with 1 to infinity. And then finally, the inflection points. Note, I didn't find any local maxes or mins for the first derivative because everything was positive, or everything was negative. If you're always decreasing, you can't have a local max or min. But you can still have inflection points. So there are inflection points 3 times at minus 1, f of minus 1, 0, f of 0, and 1, f of 1. What's the issue though? these two don't exist because -1 and 1 aren't in the domain of the function. So you might be tempted to think those are technically inflection points, but because they're not on the graph, they don't work. And then 0, 0 is your point, and that's your only inflection point. And let me make a note. Not on the graph. And that's 10b.